Welcome to the Formal Geometry 9.1 notes. We're going to be looking at circles and kind of a brief introduction to circles. Specifically, we want to talk about the relationships between radius, diameter, and circumference of a circle. So you've probably seen these two formulas for the circumference of a circle before. In different instances, sometimes you might prefer one over the other. I tend to use diameter pi more, but I think if you talk to different teachers, they might choose a different one of these that they prefer. I would say that you definitely need to get these two memorized, okay? Or if you just want to pick one of them, that's up to you, but you should identify them as being equivalent. But you want to memorize these. And again, the reason that these are equivalent is because the diameter is twice the radius in a circle, right? So just in case we're having some issues with the vocabulary, a radius is a point or is a segment from the center of the circle to any of the points on the curved portion of the circle, versus the diameter would be going all the way through the circle and would be comprised of two different radii. So a diameter can be formed by two radii, or a radius could be found by taking a diameter and cutting it in half. If you want to find the radius and the diameter of a circle with a circumference of 17, you might be using this a little bit differently than you did in past math classes. In past math classes, you probably thought of pi as around 3.14. Maybe you even took it out a couple more decimal places, I'm not sure, and you probably multiplied it all out and got a decimal answer. It's very common in geometry to leave these in terms of pi, to treat pi almost like you would a variable, and to leave the pi that's in our formulas as part of the answer. It's not the only way that things are done, and you're going to want to look at the directions on an assignment or on a test or on a quiz to find out. If you ever see the word exact, because pi is an irrational number, 3.14159, blah, 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 blah. And as an irrational number, it never ends, it never repeats. And so you can't give it an exact value without using the symbol for pi. So if you ever see the term exact, you want to keep your answer in terms of pi. However, if they ask you to round it to a certain decimal place, then you would use your calculator. So we are told that we have a circle whose circumference is 17. We want to find the radius and the diameter. You could, again, use either of these two formulas here. I prefer this one with the diameter because it's so straightforward. Circumference is just the diameter times pi. So the circumference is 17, and I could find the diameter by just dividing both sides by pi. Now, if we wanted an exact answer, that would be the exact answer for the diameter. Most people would look at that and feel like, I don't know exactly what that means. Like, I know pi is around 3, 17 divided by 3 maybe is a little bit more than 5, getting close to 6. But probably most people would struggle a little bit with that answer and not really enjoy it. So I am going to go ahead and put that into the calculator. Your calculator will have pi on the calculator. Different calculators are going to have pi placed in a different spot, but nonetheless, it's there. So I'm going to do 17 divided by pi on Desmos, and I get about 5.411268. I'll just do about 5.411. Now, we didn't have any units given to us in this particular problem. If units were given, like feet, millimeters, centimeters, I would want to include that in my answer. Since the radius is half of the diameter, I'm just going to take this value and divide it by 2. Now, the easiest way to do this so that you don't have rounding error is I already have this answer in a more accurate form on Desmos. And there's this answer button on Desmos that I could click, and then I could just divide that by 2. And that way you might notice it's pulling the previous answer to more decimal places. So I get around 2.70563. I mean, I didn't give you guys any rounding directions in this, but around 705, I believe. Check. 7056, if I round. Now, if I didn't tell you how many decimal places, then that would be an error on my part and a lack of communication on my part or your teacher's part, and you would want to ask us. On number 2, we want to find the exact circumference. When you see this term exact, you need to know that means you're going to leave pi in your answer instead of multiplying out pi as a decimal. So you are not wanting a decimal answer here. And by the way, the directions for the next problem kind of, unfortunately, a little formatting issue kind of moved over here. So super sorry about that. But that word exact, I do not want a decimal rounded answer. I don't want that. Okay, so I want the exact value. So I'm going to keep this in terms of pi instead. Again, there's two different formulas for circumference. So I could do circumference equals 2 pi r, or I could do circumference equals diameter pi. And what you might notice is this 12, and this is a square. So this 12 is all the way through the square. It's how far apart any of the two sides are. Well, that would be true even if I connect that through the widest part of the circle. That's also going to be 12 centimeters. It's like I just made like a little rectangle here, and the opposite sides would be the same. So the diameter is 12. And I want to multiply the diameter times pi, and then I do want the unit of measurement, which is centimeters. So the circumference is 12 pi centimeters. If the answer didn't say exact, I would go to the calculator and I would type in 12 pi equals to see what decimal that is. It's going to be a little bit over 36-ish. All right, number 3, you also want to find the exact circumference of the circle, but this one's interesting. It says in terms of x. Remember, the directions got moved over. I'm super sorry. Now, since it said exact, we need pi in our answer. And since it also says in terms of x, what this is telling me is we're going to have both x and pi in our answer. So why don't you pause the video and give this one a try. Something that probably should have been included in this is that this is a rectangle. Maybe before these get copied, I'll modify that for you guys. Okay, this needs to be a rectangle in order for us to do what we're going to do next. If you have a rectangle and it's inscribed inside the circle so that the corners of the rectangle are touching the circle, if you draw in the diagonal of the rectangle, it's also going to be the diameter of the circle. A lot of students will kind of see that intuitively, but maybe not know why. We're going to prove to you why this is true in a future lesson. So if I take a look at this right triangle with the 6x and the 8x for the legs, you might notice that this is a 3, 4, 5 triangle enlarged by a scale factor of 2x. So this diameter here is 10x. And since the circumference is diameter times pi, the circumference would be 10x times pi. If I had units like feet or inches, I would include that as well, but I don't. Two concentric circles are two circles. It can actually be more than two. They have to be in the same plane, the same flat surface, and they share the same center. Con means with, centric means center. This means with the same center. So in this particular example, we want to find the circumference of the larger circle. And we know that the radius of the smaller circle is 5. The circles are concentric, meaning that center is the same. So if you want, pause the video and give this a try. Well, since the radius of the smaller circle is 5, here is a location of the radius. I have a right triangle here that's kind of poorly drawn, sorry. You might not recognize this, but this is a 30, 60, 90 triangle right here. If two of the sides are 1 and 2, with the 2 being in the hypotenuse, this has to be 1 root 3, 2. This is a 30, 60, 90 triangle, maybe a little hard to identify. So this would be 5 root 3. Now, if you didn't see that, you could still use the Pythagorean theorem to find this missing side length b here, if you wanted. That would also work, 10 squared. You would be able to still do all of the computation here. A little bit larger numbers, a little bit more work. And since 75 is 25 times 3, this is 5 root 3 for this side. Same thing as we got with our ratio of 30, 60, 90 triangles for side B. And we want the circumference of the larger circle. So what we would want for the larger circle is either its radius or the diameter. Remember, there's two formulas for circumference depending on what you want to use. Well, this 5 root 3 that we just found is the radius of the bigger circle. So maybe I'll use this one just because I have a radius. So this would be 2 times pi times the radius. Now, I don't know why it's written this way. I think most of us would probably put pi at the end and maybe think of this as 2r pi. I don't know. But I'm going to go ahead and multiply the numbers and put them in the front. 2 times 5 root 3 is 10 root 3. Pi would come after that. Now, if there's a unit of measurement, I would want to include that, and there is. In this case, it's centimeters. All right, let's take a look at number 5. For number 5, we want to find the radius of each circle. And what I think is important to notice is that there's really 2 radii drawn in for each circle. For circle A, there's 2 radii, and in a circle, all radii will be the same length. In circle C, 2 of its radii are drawn in. And then in circle B, 2 of its radii are drawn in. So we have this triangle formed, but for this triangle, it's made up of really just 3 different measures that are kind of duplicated, okay, that are each used twice to form these 3 sides. Well, they've told us how big each side of the triangle is. AB is 8. BC is 7. And AC is 6. And we want to find the radius of each circle. Well, what I am going to recommend is that you start with any radius that you want and just pick one of them to call a variable. Because if you know how big one of the radii is, one radius is, you can find all the other radii because you know how much a total would be when you put 2 radii together. So maybe I'll find the radius of circle A. Now keep in mind there are 2 different radii here drawn in, 2 different radii for circle A. So I'm going to call them both x. X and the radius of circle B would combine to 8. Now you could use a system here and set up like a y variable. I just wouldn't. I think there's an easier way. You can call this radius 8 minus x because the total's 8 and part of it's x. Well, there's another radius right here. Oops, sorry. So this one's also 8 minus x. I'm going to do that same kind of thing as I label circle C. And people often call this a walk-around problem or a walkabout problem. I think I usually call it a walk-around problem. Because you're kind of walking around the circle and recognize that the radii are the same. I'm just going to actually stop and walk around in a different direction for a minute. It's not the only way to do this, by the way. I just think it's easier. Since AC is 6, and part of that's x, I could call the radius of circle C 6 minus x. And again, that radius shows up twice. And then what I want to notice is that right here, I have a really useful equation. If I combine these 2, if I use segment addition postulate, 6 minus x plus 8 minus x, that equals 7. And that gives me an equation I can solve. I'll get 14 minus 2x is then equal to 7. So 2x is equal to 7 and x is 3.5. Don't be concerned if you get a less than a whole number answer. And that's the radius of circle A. If I then know that, I can find the radius of circle B because circle A and circle B have to add up. Their 2 radii add up to 8 according to the length of AB. So I could say that circle B could be found by doing 8 minus the 3.5. So the radius of circle B is 4.5. And then if I want to find the radius of circle C combines with the radius of circle A for a total of 6 for length AC. So the radius of circle C, could be found by 6 minus x, or 6 minus 3.5. So circle C is 2.5. A couple things to notice here. This is definitely not drawn to scale, right? It looks like A should be the smallest radius, the smallest circle, but it's not. So the diagram does not have to be drawn to scale. Now, I do also want to just take a minute to mention that this equation that I chose on purpose. The reason I chose this one was I walked around my little triangle here partway by using AB and describing those radii of B. And then I stopped and I walked around the other direction to use AC. BC was the side I hadn't used yet. You might notice there is no like 7 minus x here in this expression. So I'm using that one to create my equation. Let me just show you what happens if you use one of the other ones. Like let's say you tried to maybe create your equation by using AC. You would get x plus 6 minus x equals 6. And you just get 0 equals 0, which means, yeah, that's true. But it doesn't give you any way to find out what x is. So you really do need to use the side length that doesn't have that number 7 in it. Okay, look at my expression. 6 minus x and 8 minus x. They don't have that 7 in it. That's the one that's going to be helpful to use. All right, so a little bit of vocabulary that I want to share with you. I actually mentioned one of these terms earlier. They're called circumscribed and inscribed circles. We can also use that term with polygons. So like in what it means, inscribed you can think of as like inside. Circumscribed you could think of like a circumference going around on the outside. So in this first picture here, I have a polygon that is inscribed inside this circle. And something that is true when we talk about inscribed is that the vertices of the polygon have to touch the circle if this polygon's inside. Or the circle has to touch the sides of the polygon if it's the other way around. One of those things will happen. Now, by the way, this first diagram could be described differently. We could say this has an inscribed polygon, or we could say this has a circumscribed circle. Those actually mean the same thing. Inscribed polygon means the polygon's inside. Circumscribed circle means the circle is going around the outside of the polygon and touching it at each vertex, each corner. For this next one, we could say that the polygon is circumscribing the circle because it's going around the outside and touching the circle once on each of those edges of the polygon. Or we could also describe this by saying that the circle is an inscribed circle because the circle is inside. So if you want to talk about the relationship by naming the shape that's on the inside, you would say inscribed, like an inscribed circle. If you want to talk about this relationship by describing the name of the shape on the outside, then you could say this is a circumscribed polygon. I think 1, 2, 3, pentagon in this instance. That is the end of our notes for 9.1.